Hi, my name is Dr. Joe Llama, and I'm an astronomer here at Lowell Observatory. And today I'm going to talk to you about how we find exoplanets and the history of our field and how we've gone from finding very large Jupiter-sized planets very close to their stars to the future where we're trying to search for planets just like our own. So I want to start with this beautiful image of our Milky Way. And so in the visible sky at night, you can typically see around 2,500 or so naked eye stars. So those are stars that your eye can pick up. Obviously with a camera, you can go much fainter, you can see many more stars. But one of the coolest things that we've learned in exoplanet science is that statistically speaking, every single one of those stars has at least one planet orbiting around it. So today I'm going to show you how we know that and how planets are everywhere, and we're closer than ever to the search for life in the other life in the universe. So before I talk about exoplanets, it's really useful to just remind you of the solar system and our place in the solar system. So at the center of the solar system is the sun. Then we have the small rocky planets moving out, followed by the asteroid belt. Then we have the gas giants like Jupiter and Saturn, Uranus and Neptune, and then we go to smaller bodies such as Pluto and Makemake. And until about 1995, astronomers thought this was how every solar system should look. Every system should have the star in the center, some small rocky planets near the star, followed by the larger gaseous planets further out. And it wasn't until we began finding exoplanets that we realized that this is not typical. The solar system is not special. It is not anything in particular. So how do we find exoplanets? Well, you might naively think that the only way to do this is by taking a photo of a star. And it turns out that's really difficult because stars are so much brighter than the planets that go around them. So if you take an image of just the star, all you see is starlight. It completely drowns out the signal from any planet orbiting around. And so what you have to do is you have to come up with a clever way of blocking the star's light to reveal the presence of a planet. And that's called a coronagraph. And so what you do is you place the coronagraph over the star, and that reveals any orbiting planet. And one of the poster child systems for this type of discovery is the HR 8799 system. And so here on the left, you can see the coronagraph in the center blocking the star's light. And you can see the tiny dots orbiting around, which are planets orbiting that star that are revealed by blocking the star's light. And so using this is called direct imaging, using a coronagraph. It has to be done from space, so it's a very difficult measurement to make. And we've discovered about 45 planets using this method. So another way that we can find planets is through gravitational microlensing. So here in this schematic, I'm showing you a star on the top of the image here. We're at the bottom in the Earth. And here is another foreground star. And as the star moves, it bends some of the light. And you can see as the star and planet pass between us and the background star, it lenses some of that stellar light, causing this magnification here, which is the signal of an orbiting planet. This is called gravitational microlensing. It's a very powerful technique for finding very small planets, but it's a very hard measurement to make. And so we've only discovered about 75 planets using this method. One of the most successful methods for finding planets is through the radial velocity method. And this is a method I'm going to come back to later in the talk and show you how, together with our partners at Yale, Lowell is actually leading the way in this method for finding planets. And so here you can see a star with its planet orbiting around. And you can see that not only does the planet orbit around the star, but the star is also being perturbed by the presence of the planet. And so what astronomers do is we make very precise measurements of the spectrum of the star, and we measure its radial velocity. So we measure the star pushing and pulling backwards and forwards, and the light gets red shifted and blue shifted periodically. Just like when you hear an ambulance going by, the sound gets slightly higher pitched as the ambulance moves towards you, and then it gets lower pitched as it moves away. And so this technique is very powerful for finding planets. And for a really great explanation, I'll refer you back to our Shoot for the Moon live stream last week, where my colleague Jim Cole gave a great description of spectroscopy. And so what we do is we make this measurement, and that enables us to find planets. And this was actually how the first exoplanet was found. In 1995, astronomers made this measurement of a star called 51 Pegasi. It's a very bright star. It's a solar-type star, like our sun. And what they found was that the radial velocity signal had a period of about 4 days, but the amplitude of the signal was about 100 meters per second. So from that, you can determine that your period of your planet is about 4 days, which tells you how far away from the star it is. So this is a really close-in planet. But what astronomers weren't expecting was the amplitude of the signal, the magnitude, how large that signal actually was. And so what they found was that the orbiting body was the size of Jupiter. And so they found this planet, the size of Jupiter, in a 4-day orbit around this star. So if I refer you back to our image of the solar system, we don't have any planets like that in our system. So you can imagine taking Jupiter and moving it interior to Mercury's orbit. It is completely like nothing we have in our own solar system. And so that kind of turned astronomers' views of how solar systems look like completely on its head. And so just to really impress upon you how hot these planets are, how close to their stars they are, this is an image of the solar corona taken during the fantastic eclipse we had here in North America in 2017. And I'm overplotting the image of a typical hot Jupiter scale like 51 Peg to scale. And so here you can see the planet is really close to its star. And so therefore it's incredibly hot, hence the name, hot Jupiter. And it's incredibly close. And it's a really something we do not have in our own solar system. So with the radial velocity measurement technique, we've discovered about 750 planets. And that's because that's a really intensive measurement to make. You have to study a single star multiple times. Much more convenient for finding planets is actually the transit method. Now this involves watching for shadows. And so all we do is we measure the light coming from a star, and we look for a dip in light caused by the planet moving in front of the star relative to our viewpoint here on Earth. And as the planet orbits in front of the star, it blocks a fraction of the star's light. And therefore we can infer the presence of a planet. And this is a much easier method to do because you can observe many stars at once, and all you have to do is very accurately measure the light coming from the star. Now, this is also a very powerful technique. The size of the dip that we see corresponds to how much of the star's light is being blocked by the planet. And from that, we can then infer how large the planet actually is. And so to give you some idea of reference, Jupiter moving in front of the sun gives about a 1% dip in light, which is easy to tell ground with telescopes here on Earth. However, if you're searching for an Earth-sized planet, they're much smaller. And so you're actually looking for about a 0.01% dip in light. This is a much harder measurement to make. So this typically requires space-based telescopes to make these sorts of measurements and find Earth-sized planets. And because the transit method is much simpler to use, to observe with, we found about 3,000 planets, mostly due to space-based missions such as the Kepler Space Telescope, which I'm going to talk about in a moment. But just to impress upon you again how hard it is to find this 0.01% dip in light for an Earth-sized planet, this is one of my favorite images. This is London taken from the International Space Station by astronaut Tim Peake. And what you're looking for here is one of these lights going off for a few hours once a year. That would be the way you would have to, that would be the measurement you would have to make to find the Earth around the sun. And so it's a really hard thing to do. And so one of the pioneers of exoplanet science is actually the Kepler Space Telescope. This was launched by NASA back in 2009, and its sole mission was to search for transiting exoplanets and try and find an Earth-sized planet. So Kepler stared at an area of the sky about the size of your extended fist, your extended palm of your hand, at full length on the sky. And it observed about 150,000 stars, making incredibly precise measurements of their brightnesses at very high cadence. And so in total, it measured 150,000 stars, searching for these tiny dips in light. And it was incredibly successful. And so here I'm showing you some of the planets found by the Kepler mission in a really cool movie made by a graduate student up at the University of Washington. And so what you're seeing here are the dashed lines are the orbits of the planets in our own solar system. And then everything here is to scale. And then all the other things you're seeing are the Kepler discoveries. And the planets are colored. Their size is to do with how big the planet is. So the smaller the symbol, the smaller the planet actually is. And then blue planets are cooler planets, going to red, which are hotter planets. And so you can see the thousands of systems discovered by the Kepler Space Telescope. Now, one thing you'll see here is that most of these systems are far more compact. They're much tighter in. The planets are much closer to their star than the planets in our solar system. And that's because of our method of discovery. Transits are inherently biased towards finding closer in planets. They're just much easier to find. But one thing you can see from this is that none of these other systems look like our solar system. They're all over the place. There are all types of configurations, from very close in hot planets to very close in cooler planets around cooler stars, to multi-planet systems, all sorts of dynamics. If you can imagine it, it exists in exoplanet science. So Kepler, unfortunately, didn't make it to finding a true Earth around the sun analog. Unfortunately, it had two of its reaction wheels actually failed, and so the mission lifetime was not long enough to detect the Earth, an equivalent to the Earth around the sun. So that's an Earth-sized planet with a one-year orbit around a solar-like star. So its successor is the transiting exoplanet survey satellite, TESS. And TESS launched back in 2018. And it has completed almost 2 years of data collection now. Now, TESS has a different approach to finding planets to Kepler. So Kepler stared at one patch of sky. And what TESS is doing is actually staring at multiple patches of sky. So it stares at a patch of sky for about 30 days, then it moves on. And in this way, it covers the entire sky. And so it did the southern hemisphere in the first year of operation before flipping to observe the northern hemisphere this year. And so TESS is not looking for planets like the Earth around the sun, but rather it's looking for Earth-sized planets around much smaller stars. And the advantage there is because the star is smaller, it is less luminous, it is giving out less energy. And so the habitable zone, the distance from the star where liquid water can exist on the surface, is much closer to the star. And so these low-mass stars that TESS is favoring are much more promising candidates. They're much easier to find Earth-sized planets in the habitable zone. And so this is a really cool montage of some of the systems that have been found by Kepler and by TESS. You've got everything here from lava worlds such as 55 Cancri E, super-Earths, planets slightly larger than the Earth, where the gravity is much more inflated, to planets around multi-star systems like Kepler 16b, where the sun, your shadow will always have company because you've got two shadows, to one of my favorite systems, Kepler 186f. And that's an Earth-sized planet in the habitable zone, but it's around a red star, a much lower mass star, and so it's much closer to its parent star. And so that brings me on to the search for a true Earth twin. Now, one of the closest systems we have, I've already said, is Kepler 186f. And if I show you this planet system, this is what you're seeing here in the bottom of this plot is our solar system, so the sun in the center. Mercury is within the habitable zone. It's closer to the sun than the inner edge of the habitable zone, so it's too hot for liquid water to exist. The Earth sits very nicely in the habitable zone, thankfully for us. Now, to scale above this, I'm showing the Kepler 186f system. And so its entire habitable zone fits basically within the orbit of Mercury. But again, because the star is smaller, it is giving out less energy, so that moves the habitable zone much closer in. And Kepler 186f is a planet about the same size as the Earth in the habitable zone of that planet, of that star. And so it's a really exciting system for looking for potential signs of habitability. And so just to show you again the difference, the impact of the habitable zone relative to the size of the star, here in the center is the habitable zone around a solar type star like our sun. The top plot here shows you the habitable zone around a hotter star, a larger star, and pushes it further out, and cooler stars where it moves it closer in. And so a lot of effort recently has been focused on finding planets in the habitable zone of cooler stars. But I want to talk now and shift gears and talk about actually finding a true Earth twin. So finding an Earth-sized planet in the habitable zone around a star like our own sun. And so here I'm showing all the discoveries we've made to date. So along the bottom, the horizontal axis here, is the separation of the planet from its parent star in astronomical units. An astronomical unit is the distance from the Earth to the sun. And so the Earth is conveniently at 1 astronomical unit. And then the mass of the planets we found in Earth masses. And so the Earth squarely sits here at 1,1. And what you can see is that most of the planets we found have been either much larger than the Earth, say Jupiter mass, or they're much closer in to their parent star. And we actually haven't found many planets, if any at all, very similar to the Earth around the sun. And that's just because of the tiny measurement that it's making. And so I want to move on and talk about how we're trying to change that here at Lowell Observatory and try and find this type of Earth twin planet. And so I'm going to return to the radial velocity method for finding planets. And so again, just how you have your planet orbiting your star is also slightly perturbed. And so by making this very precise measurement of the star's light, you can infer the presence of a very small or a very large planet. And here at Lowell, we're very happy to host an instrument that is exactly capable of doing this. And so this plot just shows you how hard this measurement actually is to do. So the green line here shows you the size of the signal at Jupiter very close to the sun. So the typical hot Jupiter like 51 Pegasi that I talked about before, it's around 100 meters per second, which we can make that measurement. We've been making that measurement routinely now for almost 20 years. Jupiter at its true distance from the sun, because it's further out, its gravitational pull on the sun is much smaller, and it's around 10 meters per second. But to find the Earth around the sun is the red line here. It's a tiny measurement. It actually works out to less than 10 centimeters per second. And so what we have to do is we have to design and build an instrument capable of measuring the stellar reflex motion of a planet down to 10 centimeters per second. Just think about that, and it's an impressive measurement to try and make. So here at Lowell, we're really lucky to have our 4.3 meter Lowell Discovery Telescope. And in partnership with Yale University, we've actually recently commissioned the EXtreme PREcision Spectrograph, which, as the name accurately denotes, makes extremely precise measurements of stars, trying to find Earth-sized planets. And so here is the Spectrograph Express, next to one of the graduate students from Yale who came out to help us install. And so Express is in routine operation now on the LDT, the Lowell Discovery Telescope, and it is now capable of making these tiny measurements to find Earth-sized planets. And it takes these beautiful spectra. And so here you're seeing one of our first light spectra. This was processed by graduate student Lily Zhao from Yale. And what you see is this huge array of starlight that shows you all these black features here are stellar lines that we use to measure the reflex motion of the star. And so again, I'll refer you back to Jim Cole's talk last Tuesday, where he gave a great explanation of how this is done. But there's one problem with our push to finding small exoplanets. We now have the technology to do that. We're now looking at being able to routinely make measurements of less than about tens of centimeters per second. And so instruments like EXPRES on LDT, Espresso, the European equivalent to EXPRES, are capable of doing this. But there's still one problem we have to overcome to actually find these Earth-sized planets. And that actually comes from the star itself. And so stars are not static light sources. They have star spots, sunspots. Some of you may have looked through a telescope at our Lowell campus and seen spots on the surface of the sun. And so my research interests are actually, how do we remove the signal of stellar activity, these spots and these plages, from the data we take with instruments like EXPRES to try and reveal the presence of a tiny planet. And this is really important because the amplitude of this signal can be many orders of magnitude, 10 to 100 times larger than the signal from the planet itself. And so it's crucial that we do that. And we figure out how we can remove this signal to tease out that tiny signal from an orbiting planet. And so this is a really cool movie of the sun taken with NASA's Solar Dynamics Observatory. And so you can see the bulk of the image there is the sun taken in optical, so the light that your eyes can see. If you were to go up to Lowell and look through one of our telescopes with a filter attached, never look at the sun directly, always use a filter, you would see an image like this. You would see sunspots and you'd see not much else. But as we go to different wavelengths, which this telescope SDO can observe in, you can actually see that the sun is way more active. There's the corona of the sun, which is emitting and constantly changing. And all of this activity can completely drown out the signal of a tiny Earth-sized planet. And so what we've done at Lowell is commission our newest telescope, the Lowell Observatory Solar Telescope. Now, during the night, EXPRES and the LDT, which you can see here in the background, are being used to search for planets around other stars. But during the day, until recently, EXPRES just sits idle, waiting for the night to come around to go off and hunt for more planets. And so what we've done is actually equip EXPRES with the technology to observe the sun during the day, just like we observe stars at night. And so obviously the sun is much closer to us than other stars. And so we don't need anywhere near as big a telescope as the 4.3 meter LDT. We're actually using a 70 millimeter lens. So that's a 0.07 meter optic, which you can see here in the front. And what we do is during the day, every clear day, which fortunately there are lots of here in northern Arizona, we fire up EXPRES and we point our solar telescope at the sun and we observe the sun through EXPRES just like a star at night. And the idea here is we can use this wonderful data like we see from these satellites such as NASA's Solar Dynamics Observatory to help us understand how activity impacts our spectra so that we can remove it to try and search and tease out these signals from tiny exoplanets. And as an added bonus, we will also be able to detect planets in our own solar system. And so we will detect Jupiter and we will detect Venus is our goal with the Lowell Solar Telescope. And so this is I'm very excited to show this. This is our first light spectrum of the sun. So just like I showed you the image of star 51 PEG earlier, this is the equivalent image of our sun. And so we use all of these lines to try and make a really precise measurement of the sun's radial velocity and its amplitude and its pull and push from the various planets in our solar system. We also have a really nice camera that takes full disk images of the sun in a really cool line. This is the calcium K line. And this is a well-known line for stellar astronomy. It probes the upper atmosphere of the sun. And so you get really nice definition on sunspots, on these bright regions, which are called faculae and plage. And so we will be live streaming images of the sun to the internet routinely once the telescope launches. So stay tuned for an announcement about that and how you can go and look at a live image of the sun in this really cool wavelength regime. And so that's kind of all I wanted to say about exoplanets for now. I hope I've convinced you that there is lots of exciting exoplanet science happening in northern Arizona and across the world. Lowell is home to one of the world's best telescope and spectrograph combinations for finding exoplanets. And we're just so privileged to have our partnership with Yale to have this great spectrograph here at Lowell. And our new telescope means that we have turned the LDT and Lowell into a 24-hour-a-day observatory. So at night, EXPRES will be searching for planets around other stars. During the day, we will be observing our own sun to try and tease out the impact of stellar activity on spectra. And so with that, I'm going to leave you with a really cool movie of the sun. There'll be a link to this in the YouTube description below. I highly recommend you listen to it with audio. It's fantastic. And I will wait and stay online to search and answer any questions that you may have. Okay, we have a question from David Connell, who asks, in binary star systems, are we able to differentiate between radial velocity impacts from the sister star versus any impacts from exoplanets associated with either of these stars? So that's a great question, David. So there are many ways you could imagine planets in these sorts of systems, but the typical way we found them is actually that the two stars are in the center, and the planet actually orbits both of them. And so you could actually detect that difference because the spectra of the different stars will be different. And so if the planet happened to be orbiting one of those stars, you could probably disentangle that. I don't think we've made any radial velocity measurements like that so far. And so Jim Davies asks, what is the size range for an Earth 2.0? That's a great question. And so in terms of mass and radius, it's as close to the Earth-sized mass as you can go. There is an upper bound, I believe it's around 1.3 Earth radii, above which we do not believe you could possibly host life. Okay, and John asks, can we detect surface composition like water on exoplanets? That is a great question, and yes, we can. The data that we take with spectrographs like EXPRES cover many of the atmospheric lines, these molecular lines such as water, carbon monoxide is another one that we search for, oxygen. And so instruments like EXPRES will be used to try and find out what the composition of these planets is actually like. GKC Geoscience asks, how many stars will EXPRES be able to study? So the stars that EXPRES can see, they have to be in the northern hemisphere, because that's where we are. And so we have our program where we're searching actually for 100 Earths. And so we're intensively observing 100 of very bright stars that you could see in the night sky, trying to search for Earth-sized planets. And we're complementing that with follow-up for missions such as TESS. So by adding in extra stars to try and measure the masses of planets found by missions like TESS. So many stars is the answer to that question. Okay, Tom Green asks, what velocity precision has EXPRES achieved so far? That's a great question, Tom, and we're really excited to have measured on bright stars about 20 to 30 centimeters per second. And we believe we're constantly improving our pipeline, and we believe we can push that down below 20 centimeters per second. So very bright stars. Okay, and we have another question. Any sense for searching planets in M45, the Pleiades cluster? Have anyone observed it so far? So the problem we have with searching for planets in things like the Pleiades is they're very young stars, and so it's very hard to do that, but actually people are doing that, and we are doing that as well. And I didn't have time to talk about it today, but young exoplanets are actually one of the hot topics right now in how quickly do planetary systems form. And I can't remember if there are planets in the Pleiades cluster, but our team actually found a planet in the Taurus star forming cluster. And so we found a really young baby exoplanet a few years ago. We have another question. Can you see if there is life on Earth 2.0? So that's going to be a really hard measurement to make. Missions such as NASA's James Webb Space Telescope are going to be the beginnings of making those sorts of measurements where we search for biosignatures. But I think that's going to we're a really long way off being able to do that for an Earth 2.0. But I think it will certainly be something astronomers are trying to do. Okay, and Phil Massey asks, the sun has been pretty quiet recently. When should we start seeing more activity? That's a great question, Phil. And so the recent predictions have actually said that we should start seeing sunspots later this year. And so that is typically a key that the next cycle is ramping up. And so I think from now on, we can basically expect the sun to begin getting more and more active. And I think, yeah, we should begin to see sunspots sometime towards the middle and end of this year. Okay, Michael West asks, the Earth and its large moon are sometimes called a binary planet system. Could EXPRES detect such systems around other stars? You know, that's a great question, Michael. Exomoons are one of the hottest topics right now. And in theory, you could use the radial velocity technique to detect them. That's going to be a really hard measurement to make. The way people do look for exomoons is by looking at the brightness change. So you could imagine as the moon orbits around its planet, it will block the amount of light the star emits will get blocked by different amounts depending on the configuration of the Earth-Moon system. And there are astronomers searching for exomoons. So far, the search has been unsuccessful, though we have a few really promising candidates that are being followed up right now. Okay, well, I hope I've convinced you that